Good day, guys. I hope you are enjoying the vacation that we are having right now. And once again, thank you so much for participating in our research. And for those who are not in our experimental group, meaning that you have not been taught the intervention that we promise you. But today, I'm going to discuss the alternative atom technique for balancing chemical equations. Once again, uh, I'm Sir Andre Canales, one of your researchers, and let's learn about um, this method. So at the end of this video, you are expected to balance chemical equations using the atom technique. But first, let us discuss what is law of conservation of mass. So, the law of conservation of mass states that matter cannot be created nor destroyed, meaning that in a chemical reaction, the total mass of the reactants must equal to the total mass of the products. So, it must be balanced on both sides, the atoms of each element. So for example, we have hydrogen reacting with oxygen. The product will be water, which is H2O. So according to this law, the number of atoms per element must be equal. So as you can see in our reactant side, there are um, two atoms for hydrogen and two atoms for oxygen. But if we're going to look at the product side, it is true that we have two hydrogen atoms, but we only have one oxygen atom. So this is an unbalanced chemical reaction. So what we are going to do is to put a numerical coefficient before the substance in order to balance the equation. So we're going to put 2 in here. Then we're going to have uh, 2 oxygen atoms and 4 hydrogen atoms. But as you can see, the equation is still not balanced since we have to put another coefficient here. Now we can say that this equation is balanced, that the atoms in this chemical reaction do not magically appear or disappear, that this abides the law of conservation of mass. And what I showed you actually is a very common method of balancing chemical reaction known as the trial and error method. So when we are balancing different unbalanced chemical reactions, we are trying to think of coefficients that will somehow balance the atoms on both sides per element. For example, we're going to write each of the element here. We have the carbon, the hydrogen, and the chlorine. So for the reactant side, we have one atom of carbon, four atoms of hydrogen, and two atoms of chlorine. But on the product side, we have uh, one atom of carbon. We also have one atom of hydrogen, but we have technically we have four atoms of chlorine here and another one on the chloric acid. So what we are going to do is to to guess coefficients that will somehow uh, balance this chemical reaction. So we're going to, for to save up some time, we're going to put um, 4 in here to balance the hydrogen atoms. Then we're going to put 4 in here too, because as we can see, if we're going to put 4 in the hydrochloric acid, we will be having um, 4 plus 4, we will be having 8 atoms of chlorine. So in order to balance the number of chlorines here, or the number of atoms per chlorine here, we're going to put the coefficient 4 in here. So as you can see, the equation is already balanced. But realistically speaking, um, it looks very easy because we already know the coefficients to put in there, and the chemical equation is somewhat simple. But if you are going to encounter a chemical equation and a balanced chemical equation, such as the equation for photosynthesis, let's say. As you can see, there are a lot of elements, and it's quite complex in comparison with this uh, chemical equation. And if you do not memorize the coefficients for this reaction, you will take a lot of time trying to balance this equation. However, since you participated in this research, we are going to offer you a somewhat alternative method that is more time-saving, and uh, you're just going to follow some sort of formula in order to determine the coefficients necessarily to balance the atoms in the reactant and product side. So you're not just going to use different types of numerical coefficients or guess them, because that would take up too much time. And this is what we call the atom technique. But what does the atom technique stands for? Actually, when the atom technique, it serves as some sort of mnemonics for the algebraic way of balancing chemical reactions. And in atom technique, you're going to follow these 4 steps. Number 1 step is to assign a coefficient. Variables, rather. Sorry. Assign variables. Then T stands for translate into equations. One is the value of a variable. M and M stands for match the number of atoms in each element. So how does this work? So we're going to go back in the previous example that I gave you. The reaction between methane and chlorine to produce um, uh, carbon tetrachloride and hydrochloric acid. So what you're going to do using the atom technique, let's follow the atom technique, is first is to assign variables. These coefficients we must use literal coefficients, not numerical coefficients. What do I mean by literal coefficients? So if you know your algebra, literal coefficients are coefficients that are letters. Let's say that um, the coefficient for methane will be A at first, then B in here, C in here, and D at this hydrochloric acid. Okay, so that is the first step. That is to assign these literal coefficients in this chemical reaction. Then we're going to translate them into equations. How are we going to do that? First, you would want to enumerate the elements involved first. So we have the carbon, we have hydrogen, we have chlorine. Then after listing the elements, we're going to translate them into um, equations. So we only have the subscript 1 in here. Of course, if you know your chemistry, you already know that there is automatically 1 in there. So 1 times A, that will become A for carbon. And this arrow here will always serve as your equal sign. Okay? So in our third substance, we can see that there is also carbon in here, meaning that there is a 1C in there and no more carbon. Now let's move on to the hydrogen atom. So in our first substance, we have 4 hydrogen atoms. So 4 times A, we have 4A. Then on our second substance, we do not have hydrogen atom, and we're going to put the equal sign. Let's go to the product side. On our third substance, there is no hydrogen atom again, so we're going to move on to the fourth substance, and we can see that there is a 1 hydrogen atom there. So 1 times D would become D. Now let's move on to the chlorine. So as you can see in our first substance, there are no chlorines in there, so we're just going to skip them. On the second substance, on the other hand, has 2 atoms of chlorine, so we're going to multiply them. So 2 times B, we're going to get 2B. Then put the equal sign, and in here, on the third substance, uh, we have 4 chlorine atoms. So 4 times C, we're going to get 4C. And lastly, in our fourth substance, the hydrochloric acid, there is a 1 chlorine atom there. So 1 times D, we're going to get 1D. So that is how you translate them into equations. Now that we are done with the second step, let's move on to the third step, which is 1 is the value of a variable. So actually, you can pick any variable in here, but for formality, let us always use, since it is much easier to use a as the value of 1. So let's say a is equal to 1, then we can immediately tell that C is equal to 1 as well. And we can also get the value of D in here by substituting A with 1 in the expression. So 4 times 1, the value of D will become 4, and the value of B, we can actually get the value of B by uh, replacing uh, or substituting the values of C and D that we obtained from the previous computation. So the value of C is 1, so we can immediately tell that this is 4, and the value of D is 4. So 2B, uh, 2B is equal to 4 plus 4, that would become 8. And if we're going to divide both sides by 2, we will obtain B is equal to 4. Now that we are able to obtain all the values in there, we can use the uh, we can move on to the last step, which is to match our equations. So you're just going to substitute all the value that we got. So for letter A, we have 1. So we can just oh no. We could just put the coefficient 1 in here, or put nothing at all, because automatically it tells us that the coefficient in here is 1. For letter B, the for letter B, our coefficient is number 4. And for our letter C, our coefficient there is 1 also. And lastly, for our letter D, the coefficient there is 4. So as you can see in here, it is similar to the variables that we obtain from the use of trial and error method. And I know it seems hard at first, but if you really mastered using the atom technique, it's quite more practical in comparison with the trial and error method. So I am encouraging you to try to balance many chemical equations as much as possible using the atom technique. So let's have another example. Let's go to the complex one, which is the equation for our photosynthesis. So this is the equation for our photosynthesis, which we have carbon dioxide um, reacting with H2O to produce glucose and oxygen. So if we're going to follow the atom technique, we know that we have to assign, the first step is to assign variables in each substance. So we're going to put A in here, B in here, C in here, and D in here. Now after putting some literal coefficients or some variables before each substance, we have to translate them. Second step is translate them into equations. We're going to enumerate once again the different elements involved in this reaction. We have CO, carbon, oxygen, and hydrogen. Then after translating them into equations, we're going to we have not yet we have not yet translated them into equations. So we're going to multiply the coefficient of carbon there to A. So we have A, there's no carbon in here, equals sign. We have 6 times C, we're going to have 6C. And nothing else. Next, let's go to the oxygen. So we are going to multiply two atoms of oxygen here, 2A, 2A, and one atom of oxygen here to B, equal sign, six atoms here to C, 6C, and two atoms here to D. Next is the hydrogen. So we're going to multiply two atoms of hydrogen here to B, and plus sign, and 12 atoms here of hydrogen to C. Now, after translating them into equations, we are going to conclude that 1 is the value of a variable. Again, let's do what we did in our previous discussion. The value of A is equal to 1. So we can immediately conclude here that 6C, the value of C in here will equal to 1/6, a fraction. Let's try to do this one once again in this letter. So we already know the value of C rather. We already know the value of C, which is 1/6. So 12 multiplied to 1/6. That would give us the answer of 2. But this 2 will be divided by 2 in here since we have 2 before the B. So our B is equal to 1. Now let's go to this equation. We already know the value of A and B. Again, the value of A is 1. So 2 times 1, that will be 2. And the value of B is 1. On the other hand, here on C, we already know the value of C, which is 1/6. So if we're going to substitute 1/6 in here, we have to cancel this out, and we are going to obtain the value of 1. So as you can see in here, we can subtract 1 on both sides. Or in the informal term in mathematics, you have to transpose here in there, and it will become negative 1. And that would leave us to 2D is equal to 2, and if we divide it both sides by 2, we're going to get, D is equal to 1. Now, one rule that you must remember is that numerical coefficients cannot be in a fraction form. It must be a whole number. So in order to make the value of these coefficients into whole number, we're going to multiply them by the denominator of value C. Because if you multiply this by 6, it will already become a whole number. If we multiply this by 6, we're going to get the value of C as 6. If you multiply the value of A by 6, we're going to get the value of A as 6. Or if you multiply the value of D by 6, you will get the answer 6, and so on and so forth. Or if you so you could just match the equations now that um, we're able to solve. So for carbon dioxide, we have the value of 6 carbon dioxide. Or in H2O, we will have 6 H2O. In our glucose, we're just going to have one molecule of glucose, and for our oxygen, we have the molecule of oxygen as 6. Actually, you could just, if it's more easier for you to just multiply them once. Remember that we obtain 1 in for letter A, for letter B 1 in here, for C 1 over 6, and for oxygen we got, or letter D we got 1. You could just multiply this entire equation by 6 like we did, if you prefer this more orderly manner. So let's check if our answer is correct. So in our reactant side, we have 6 carbon of 6 atoms of carbon. Rather, sorry. On our product side, we have 6 atoms of carbon. In our reactant side, we have 2 times 6, we have 12. 0 times 1 times 6 is 6. So 12 plus 6, we have 18 atoms of oxygen. In our product side, we have 6 atoms here. That's 6 times 2, 12. So that will be 18 atoms of oxygen as well. And for hydrogen, we got 12 atoms of oxygen in the reactant side, and 12 atoms of oxygen in the product side. So this equation is already balanced. So if it's alright by you, you can try to practice balancing these chemical reactions. And it's on you if you want to comment down the answers or try it out by balancing the following chemical reactions. I'm just going to comment if your answers are correct. Oops. So thank you very much. If you have further questions, please contact me in my Facebook account, or you can chat in our GC. You can also ask my fellow researchers, Miss Hanilin Poyawan, Miss Nicole Roque, and Miss Kisha May Lamsen. Thank you so much. Have a good day. Bye.